الله الرحمن الرحيم. Hello everyone. I am going today to calculate the currents for an asymmetrical system by using the phase quantities and by using the sequence components. Here, as you see, an example for the calculation of the currents by using the two mentioned methods. We have a star connected voltage source with the following imbalance voltages. The imbalance voltage is applied to a delta connected load and to a line impedance. The delta connected load has an impedance of 30 ohm with an angle of 40 degrees, and the line impedance is 1 ohm with an angle of 85 ohm for each phase. The generator neutral is grounded to the earth through an impedance of J10 ohm, and the generator sequence impedances are G1 ohm for the zero sequence impedance and J15 for the positive sequence impedance and 3 ohm for the negative sequence impedance. Now we want to calculate the currents. The IA and IB and IC. We start the calculation by using the phase quantities. Firstly, we convert the delta connected load to an equivalent star connected load. The star connected load in this case is equal to the delta connected load divided by 3, and we have in this case the following diagram. As you see, this is the star connected load equivalent to that of the delta connected load, and this is the source with an unbalanced with an unsymmetrical voltages, as you see, and the neutral point of the generator is connected to earth through an impedance of Zn. Now we have to choose 3 closed loops. Loop 1 is, as you see, n started from n, a, n capital, e, n. This is the first loop. N, A, N capital, Earth, N, the neutral point of the generator. The loop number 2 is N, B, N capital, Earth, N. And the loop number 3 is N, C, N capital, E, N. We have 3 loops. From each loop, we can apply Kirchhoff's voltage law. Applying Kirchhoff's voltage law from the first loop, we can write the first equation, the first independent equation, 277 0 angle volt. Okay, is the drop voltage between this point and this point, between the N small and A. And the drop voltage between A and N capital is equal to 1 multiplied by the current IA plus the voltage between the neutral point of the load and the earth, V between N and A, between the neutral point of the load and the earth and the ground, plus the drop voltage between E and N, plus Zn multiplied by the neutral current equals to 0. This is the first equation. And the second independent equation from the loop number 2, minus 260 with an angle of minus 120 plus drop voltage over the line impedance and the load impedance. Multiplied by IB plus drop voltage between N capital and the A plus Zn In equals to 0, because the second independent equation, and the same from the third loop, minus 295 same IC plus Zn In equals to 0. Equation number 3. So we have 3 equations, 3 independent equations with unknown variables as you know, IA, IB, IC, and the unknown VNA and INS also. Now applying Kirchhoff's current law, node N point of the load, the summation of the currents is equal to the neutral current. So IA plus IB plus IC equals to the neutral current, IN. This is the equation number 3. Applying the second law, Kirchhoff's current law. Since the neutral point of the load is isolated from the ground, N equals to 0. Neutral current in this case is equals to 0. Okay. And also we can write that Zn multiplied by N equals to 0. So this term and this term are zeros. In equals to 0, that means that IA plus IB plus IC equals to 0. Equation number 6. Seven. We have 7 equations. Now, adding up equations number 2 and 3. So, equation number 2 plus equation number 3 to the following equation: minus 260 minus 295 voltage C 10 multiplied by IB plus IC. These two terms are added up, plus 2VNE equals to 0. This is equation number 8. As you know from equation number 7 that IB plus IC equals to minus IA. Okay? Then instead of IB plus IC, we write minus IA. Then equation number 8 becomes as follows: minus 260 minus 295 115 minus 185 degrees plus 10 angle of 40 degrees multiplied by IA plus 2VNE equals to 0. Equation number 9, from which we can find, okay, this is the equation number 9. Now, adding equation number 9 plus equation number 1 equation number 1 plus equation number 9, we can write the following: minus 277 volt, voltage of phase A, minus the voltage of phase B, minus the voltage of phase C, okay, 2VNE plus VNE equals to 3VNE equals to 0. This is equation number 10, from which we can, okay, from equation number 10, we can write that VNE is equal 1 divided by 3 of multiplied by the phase voltage of A, voltage of phase A plus the voltage of phase B plus the voltage of phase C. Equation number 11, from which we can calculate VNE and the value, the result of the summation of the these three voltages divided by 3 is equal to 15.912 with an angle of 62.11 degrees volt. This is the voltage of the this is the voltage between the neutral point of the generator and the earth. Voltage between the neutral and the earth. Now, since we know the voltage of VNA, we can obtain the current in phase A. So, substituting equation number 11, okay, into equation number 1, we can find that IA is equal to the voltage of phase A minus the voltage between the neutral point of the load and the ground divided by the line plus the impedance of the load. IA is equal to 25.15 with an angle of minus 46.76 ampere. This is the current of phase A. This is the current of phase A. And by the same manner, we can calculate the current in phase B. IB is equal to, IB is equal to the voltage of phase B, 260, with an angle of 120, minus the voltage between the neutral point of the load and the ground, divided by the impedance of the line plus the impedance of the load. This value is equal to 25 also, 0.71 with an angle of 196.334 ampere. And the same for the current IC is equal to the current of phase C minus 15 point divided by equals to 26 6 point 62 angle of 73.76 ampere. So these are the currents in the line using the phase quantities. Using the phase quantities. Phase quantities. Okay. Now we want to calculate these currents also, but by using the sequence quantities. By using the sequence quantities. This is the second method of calculation. First of all, to calculate the currents, we need to find the sequence components, sequence quantities each of the line and the load, each component of the system. We have three components in the system. We have the generator, we have the line, and we have the load. For the load, start by the load. Load for the load, for the line, the zero sequence impedance equals to the positive sequence impedance equals to the negative sequence impedance and equal to 185 ohm. This is for the line. Now for the load, the delta connected load, the positive sequence impedance equals to the negative sequence impedance and is equal to Z delta divided by 3. Divided by 3 and equals to 10 ohm, while the zero sequence impedance for the delta connected load is equal to Z delta divided by 3 plus infinity. Okay? Plus infinity. That means the circuit between the neutral point of the load and the earth is opened. Open. Okay. Now, for the generator, note for the generator is equal to G naught plus 3Zn. Zg naught for the generator is 1 ohm and Zn equals to 10 ohm. So equals to J1 plus 3 multiplied by J10. This is the zero sequence impedance for the generator. And Z1 for the generator, G1 for the generator is equal to 15, G2 equals to J3, J15, and G2 equals to J3 ohm. Since we obtained the sequence quantities of the load and the line and the generator, now we need the sequence quantities of the source voltages. We have VA equals to 277 and VB equals to 260 minus 120 degrees. VC equals to 295 volts. Now, from the formula, as you know, VS equals to the inverse of A multiplied by the phases. These are the phases. We have 3 voltages. So VS V1, V2 equals to the inverse of A, the inverse of A, 1 divided by 3, 1, 1, 1, 1, A square, 1, A square, A, multiplied by V phases, 277, 260, 295, 150. V naught equals to 1 divided by 3, summation of the voltages, voltage of phase A, B, the voltage of phase C. This is equal to, as you see, 15.12, an angle of 62 volt. This is the zero sequence component of the voltage VA. Okay, this is the zero sequence component. While the positive sequence component is equal to 277 plus 260, the phase voltage of phase B multiplied by A. That means this voltage is rotate anticlockwise by 120 degrees, plus the voltage of phase C multiplied by A square. That means that the voltage of phase C rotates anticlockwise by an angle of 240 degrees. So V1 is equal to 277.1, an angle of minus 1.77 volt. And the same for the negative sequence, the voltage, okay, the same, but the voltage of phase C is multiplied by A square, multiplied by A square. And the voltage of phase C is multiplied by A. So V2 equals to 9.218 with an angle of 216.59 volt. These are the sequence components of the voltages of the source. The sequence components of the source volts. Now we can draw the sequence networks of the system. Okay, sequence networks of the system. We have for the zero sequence network the voltage V0 and the zero sequence of the line, zero sequence of the load. Okay, like this, as you see in this diagram. This is the zero sequence network for the system. This is the zero sequence voltage of the source. This is the zero sequence of the line. Okay, and this is the zero sequence of the load. As you see, we have here an open circuit, which means that the impedance between this point is the neutral point of the load, and the neutral or the earth is this impedance is equal to infinity. Okay, you must remember that in delta connected load there is no connection between the neutral point and the earth, so the path for the zero sequence current is open. We have an open circuit for the zero sequence current. And this is the positive sequence network. We have the positive sequence voltage of the source, the positive sequence impedance for the line, the positive sequence impedance for the load. And this is the negative sequence, the current, the negative sequence voltage, negative sequence impedance for the line, the negative sequence impedance for the load. From these networks, we can find that I naught, as you see, since the circuit is open here, I naught is equal to 0, while I1 from the positive sequence network, we can see that the positive sequence voltage is applied to these two impedances. We have a voltage of 277 minus 177 volts over divided by 185 plus 10 with an angle of 40 degrees. This current is equal to 25.82, angle of minus 45.55 ampere, and the negative sequence of the current equal to, we have voltage here applied to the impedance of the line and the impedance of the load, 9.218, an angle of 216 divided by the impedance of the line and the impedance of the load, and I2 is equal to 0.859 here with an angle of 172.81 ampere. Okay, these are the sequence components of the current IA. As we know, the current of phase A is equal to the zero sequence component plus the positive sequence component plus the negative sequence component, and IA in this case is equal to 25.15, an angle of minus 46.776 ampere. It is exactly the same value that obtained by using the phase quantities. This is the phase current of phase A using the phase quantities. Same value. Now, the same we can calculate in the same manner. Calculate the current of phase B. IB is equal to I naught plus A square I1 plus A I2, means equals to 0. I0 is equals to 0 plus I1 multiplied by A square, 25.8 multiplied by A square. This means that the current I1 rotates anti-clockwise by 240 degrees. 240 degrees plus I2 multiplied by A, 0.59 angle plus, it is multiplied by 8 means that it rotates anti-clockwise by 120 degrees. IB in this case, IB equals to 25.7 with an angle of 196.34 degrees. IB in ampere. This is the same as you see when we calculate IB in phase quantities by using the phase quantities, and also the same for calculating IC. IC equals to I naught plus I1 plus A square I2, and we conduct the calculation by the calculator. We find that IC equals to 26.60 angle of 73.77 ampere. So, as you know, we calculate the phase currents by two methods. The first method is the phase quantities, and the second method by using the sequence quantities. And we see when we use the sequence, when we use the phase quantities, by using the phase quantities, the three equations. Here, the three equations. By means we can find IA and PIC. These equations are coupled, and the calculations, as you see, is the calculation is tedious and time consuming. While by using the sequence components, as you see, these equations are decoupled, and the results obtained easily without any complications. So we can say in symmetrical systems, if the system is symmetrical, it is preferable to use the phase quantities if the system is symmetrical. But if the system asymmetrical, it is preferable to use sequence quantities. This is what I want to say in this lecture. Let us stop here. Goodbye, everyone, and see you later in next videos, inshallah. Wassalamu alaikum wa rahmatullahi wa barakatuh.